Number 6. So there's two parts to number 6. We have a top and the bottom. Just reread it so you know what I'm referring to. Okay, so the slight variation here, we're dealing with top and bottom, and the question is what's the tension? So let's draw the free body diagrams at the top and bottom. So this is what I'm going to draw in right away, FG. I know it's included in every free body diagram, and always pointed down. That doesn't change. And then at the top, there's a tension. It's different than the tension at the bottom. It doesn't, smaller, it's less. It doesn't have to be as great because it's acting with gravity. Gravity's assisting it. At the bottom, FT2 is greater because it has to act against gravity, has to overcome gravity. So we'll deal with, in part A, free body diagram 1 at the top. So free body diagram 1, you don't have to do this part. You do have to provide a free body diagram with these problems. So do that for the sake of the marker, right? So I can go back and give you some marks to see whether you're on track, at least on track with the diagram or not. If you're going to skip right to the equation, I'm going to mark you simply on that. So draw the free body diagram. Now, this part here is adding the vectors. Well, let's see when I add the vectors for the top. They're in the same direction. They add tip to tail. The resultant is drawn from the tail of the first to the tip of the last. That's my F net. Okay. What's it equal to? What's my F net equal to? My F net is my FC. Same thing. FC is just a special type of net force. It's equal to, just add them up. Okay, so that's my centripetal force. We always know this equation is true, independent of what the free body diagram is. That's true. For this particular case, FC on the left is FT1 plus FG. On the right side, now pay attention, closer attention to this. The expression we use for the acceleration depends upon what we're given. We're given the speed, if we're asked to solve for the speed, we use v squared over r. The other alternative is this. That's the alternative. Why did I decide to use this? Because if you look at the question, it says the time of one revolution. Time of or for one revolution. It's the same thing as period. That's the definition of a period. The time to go around once, to repeat the pattern. One revolution is a repeating pattern. So this is the same thing as period, which we label big T, uppercase T. Okay. So let's just plug in what we've got. I'm going to rearrange for the tension. Minus Fg. Okay, I'm going to erase it. Fg is the same thing as mg. I'm going to use the mass. This is tension. Or, pardon me, this is period. That's period. I even got confused. This is a subscript referring to tension. It's two different things. Okay, just plug in your values. The period has to be in seconds, which it is. This works out to be 71 newtons. Interesting. Okay. That's for part A. Part B. What's the tension at the bottom? Okay, at the bottom, look at the diagram. The bottom is here. Okay, so I'll redraw the free body diagram. I'll scroll down. With a smaller FG, FT2 has to be this, has to be bigger. So that what? So that you get a net force towards the center. FT2 has to be bigger. So that when you add them tip to tail, your net force is up or towards the center of the circle. Center is here. So the net force has to be up. In order to do what? To keep this object moving in, keep it moving in a circular path as opposed to straight. We don't want that. We want it to move in a circular path. Okay, so F net is equal to FC, which is equal to FT2, not plus anymore, minus. Because it acts in the opposite direction, it's going to give you a net force that's smaller than FT2. Same equation on the right. I can write MA, but I know that it's going to be this expression. Because of what I'm given the period. So this is our expression. You're going to rearrange for FT2. You're going to now add the FG, not subtract it, on the right side. It's going to be added on the right. Subtracted on the left, now it's added on the right. I'm going to erase it, save myself a little extra step, just put mg. Plug in before, as you did before. This was supposed to be squared, by the way. Plus 2.2. Okay, so this works out to be, should be more than what we had here. Should be more than that. It is. Okay. Which is what we expect. The tension at the bottom is going to be greater. Okay, I'm going to set up a video. I'm going to start. This is related to, it's still part of circular motion, but we have to get a little more. We're now going to deal with circular motion of satellites and moons. The circular motion of our own moon or circular motion of our satellites that we take for granted depends on gravity in the bigger sense. When we're dealing with satellites, it's no longer m times 9.81. That is no longer the case. This value is going to reduce. As you get farther above the surface, like near where the satellite is, this value is much less than 9.81. So we're going to deal with that, and we're going to apply it to circular motion of the satellite as it moves about the Earth. But we have to first of all talk about what's the new expression for FG. So we'll get into that in a minute. If you can just look or try number 8 on page 229, do that. I'll come back to that probably later because I got to move on to gravity. But try that out while I'm setting up, because I'm going to find you a good video for a good introduction. Do not. Yeah, I'll link this one. This is good. Very good video. Got it. Mm-hmm. Number 8. Yeah.
What the hell in this case?
It's a weird diagram. Yeah, guys, for number 8, it's a. You'd never have that in real life. What they should have drawn is this. I would replace that diagram in number 8 with this. Just replace it with a hill. And number 8, replace it with a hill. And that, you have FG acting down. And because this person is on a surface, there's going to be a normal force pointing towards him or her. It's going to be less, has to be less. In order for what? In order to get a net force towards the center. So that what? So that instead of moving this way, we move along the curve. Yeah, this is not as good. I like Professor Anderson, but give me another couple minutes and then we'll go through an explanation of gravity. Ah. We'll start in a sec here. I'm going to upload videos for you. Come on, load, you dumb thing. Okay. Sorry, just trying to do this for you. Not working. Almost done. Done. Okay. Here we go. We're going to watch this video. It's an introduction to gravity on a large scale. You want to write down the title. Okay, so it's, I would, universal gravitation constant. I would reword this universal, I'll write it on the board. Okay, yeah, you may have done it. Some of you may have, you should have done it, but it's Newton's, based on Newton's ideas, universal, which means it's applicable everywhere. Law of gravity. Newton's universal law of gravity. That's the title. Okay. Now it's true. It's still true. This is the force of gravity. But this, as I said earlier, can change. If you're near the surface, it's a constant. Near the surface of the Earth, it's 9.81 on average. As you get much farther away, it's even noticeable on the top of Mount Everest, this value will decrease. You get really far away, like a satellite hovering above and orbiting above the surface, it's far less. You have to be able to calculate it. You need a more universal equation. This equation is applicable to any objects. It's not just the Earth and its satellite. It's any two objects. You could calculate the force of gravity between them. So that's why it's applicable everywhere, in any situation. So we'll make some notes on this as we go along. I'll stop and I'll highlight the important stuff. You can add to whatever. I'll highlight the important things. What's going on here?
Let's look at some problems. Calculate the force of gravity that exists between a 60 kilogram person and an 80 kilogram person, or 50 centimeters apart from each other. So let's draw a picture. So let's say that this is the 60 kilogram person, and here is the 80 kilogram person. How can we calculate the gravitational force between the two?
Okay, so you want to calculate, you need a universal equation, applicable everywhere between any two objects. Calculate the force between these two persons. You need a more universal equation. That's what we're going to look at. Could be any two objects, not just two people. Could be, yes, the Earth and a satellite, the Earth and the Moon. Between any two objects. Anywhere in the universe. Okay, so that's your question. What have we discovered? All discovered through experimentation, verified, Newton came up with, verified through experimentation. Newton came up with the idea by looking at data.
Now, gravity is a force of attraction. Gravity brings matters together. So gravity is going to pull the 60 kilogram person towards the 80 kilogram person. And the 60 kilogram person exerts a force on the 80 kilogram person. And so these two forces, they're equal in magnitude but opposite in direction.
Okay, so you want to make a note. This is an important note. Both of them exert a pull on each other. They both experience a pull from the other person. And that force that they experience is the same in magnitude, but opposite in direction. The 60 kilogram feels pulled towards the 80 kilogram. Pulled. Like, it's a very, very, you don't experience it, but Jake is in behind you. Believe it or not, there's a very small gravitational force pulling you towards Jake. It does exist. It's minute. Now, they had to do very, very precise experiments to measure it for small objects. It's really only noticeable for bigger objects, but you can still apply it to smaller objects. And yes, it's measurable with precise instruments. They've done it.
And this represents the force of gravity. Now, the way to calculate it is to use this equation. It's equal to g times the mass of the first person times the mass of the second person divided by the distance between them. And that distance has to be squared. Now, the distance between them is 50 centimeters. And we need to convert that to meters. 1 meter is 100 centimeters. So 50 centimeters is equivalent to 0.5 meters. You got to divide by 100.
So make a list of what you've got in this problem so far. You got the two masses. You can call that M1 is 60 and M2 is 80. And the distance between them is 0.5. Doesn't matter which one you call 1 and 2. They're interchangeable. But we'll call, I think he's going to use M1, or object 1 is the 60 kilogram. So we'll stick with that.
G is the universal gravitation constant. It's 6.67 times 10 to the minus 11. And the units are newtons times square meters divided by square kilograms.
Okay, so this is a constant that they measured and they found was a constant. It's the same value between any two objects, whether we're talking about the two people or even the moon and the earth. Same constant. It's universal. It's called a universal constant because it's the same. We think it's the same everywhere in the universe. It's very small. You notice the exponent, 10 to the minus 11. Yes, you'll be given this. This is on the back of your formula sheet. You're given that constant. You have it. Why don't you check for that now? Once you get your formula sheet out, just verify it. Turn to the back of the formulas. Turn to the back of the formula sheet. Take a look where it is. It's in your formula sheet. Okay, everyone know where it is. Get familiar with it because you do need to use it. So know where it is on the formula sheet. You're going to use the same formula sheet on your tests, same one on the final. So that's where it is. Know where it is. Take a look at what else is on. It's a table of constants. That's what it is on the back side of the formula sheet. Take a look at what else it gives you. It gives you the mass of the Earth. See if you can locate that.
How did they find that?
They've extended. They've found this obviously formula is applicable between larger and larger objects. So they've extended this formula to the Earth. So they've used this formula to calculate the mass of the Earth. I can look it up. There's probably other ways of determining it as well. It's not just one way, but this equation would be one way of determining it.
They put the Earth on the bathroom scale.
Exactly. They put the Earth in a bathroom scale. I mean, we'll look at different ways they've determined it, but this is definitely, this equation is one way they determine it. Okay. Look at what else isn't contained in your table of constants. You also have the radius of the Earth. Okay. Radius of the Earth, make sure you distinguish that. I think you also have the orbital radius. Is that right? Is the orbital radius there? Make sure you clarify that. You're clear on that. There's a difference. Is the orbital radius there? You should have the radius of the Earth. You should have the mass of the Earth. Do you have the orbital radius of the Earth?
Orbital radius?
Yeah, in the old one we used to include orbital.
Like around the sun?
Around the sun. Is it there? Okay, so make sure you understand the difference. Orbital radius is the average distance from the sun. The radius of the Earth obviously is half the diameter of the Earth. And there's a difference there. Notice also you have the mass of the sun. That should be there. See the mass of the sun? Should be there. Mass of the moon. Okay, so that's all there for you. Those are givens. And then make sure again you know where the universal gravitational constant is. Big G.
So let's go ahead and calculate the gravitational force. So it's going to be 6.67 times 10 to the minus 11 times the first mass, which is 60 kilograms, times the second mass of 80, divided by the square of the distance, which is 0.5 meters squared. So the answer is very small. It's 1.28 times 10 to the minus 6 newtons. So that's the force of gravity.
Okay,
between these two.
so that is approximately, look at how small that exponent is. It's 10 to the minus 6. That means whenever you see 10 to the 6, 10 to the 6 means you've got $1 million. 6 zeros, $1 million. Minus 6 means one, it's a fraction, 1 over 1,000,000. So the force between these two persons is 1/1,000,000th of a Newton. That's why you don't notice it. It's really, it does exist. Okay, Hugh and Marielle are sitting next to you. There is a gravitational force, but it's very small. What really affects the smallness of this force? It's this constant here, 10 to the minus 11. Such a small exponent. That's resulting in a very weak gravity. So how do you overcome that? Why do we see the effect of gravity on a more massive scale? Because on a more massive scale, these masses are bigger. At least one of them is. You're dealing with the mass of the Earth. Take a look at the exponent of the mass of the Earth. 10 to the what? It's the mass of the Earth. You tell me, I didn't memorize that one. What is it? 10 to the 24? Yeah, big. So that is why you see the effect of Earth on you, because the mass of the Earth is big compared to the universal constant exponent.
Number 2, calculate the force of gravity of a 25 kilogram block resting on the Earth. And we're given the radius of the Earth.
Let's get through this. And
So let's say
was it a
this-
simple question? Or?
Can you go back to
Yeah. It's freezing on me. How come it's doing this? You got it.
So that's the force of gravity between these two individuals. Number 2, calculate the force of gravity of a 25 kilogram block resting on the Earth. And we're given the radius of the Earth. So let's say this is the Earth. And we have a block resting on it. What's the force of gravity that is exerted on that block, which points towards the center of the Earth? How can we calculate it? So to calculate the gravitational force, we can use this equation. G m1 times m2 over r squared. So G is 6.67 times 10 to the negative 11. And the mass of the first block is 25. The mass of the Earth is 5.97 times 10 to the 24 kilograms.
Okay. Now he's not finished yet, but these are interchangeable. You could call whatever you want 1. Doesn't matter. It's like 2 times 1 is the same thing as 1 times 2. So whatever you want, you can call the object number 1. He's called object number 1 the block. Object number 2 is the Earth.
And the distance between the center of the block.
What is he going to use for the distance? The block is on the surface of the Earth. Do you have the distance? It's not in the, is it? Okay, he gave it to you. But let's say you didn't have it, you'd look at your formula sheet, the back of the formula sheet, it's there. Look at the size of the radius of the Earth, approximately 6.4 million, 10 to the 6 million. Pretty big. 6.4 million meters. It's huge.
And the center of the Earth is approximately the radius of the Earth. The block is going to be relatively small, so we can say it's about the radius of the Earth, which is 6.38 times 10 to the 6. And don't forget to square it.
Okay,
So let's type
it's going to get a little confusing later on. Make sure you're clear on this. For this particular formula, for calculating the force of gravity, the radius is squared. Later on, we'll deal with potential energy. It's not squared, it's simply just R. So make sure you're clear on that. Universal gravitational constant. It's this value, it's on the back of the formula sheet. 6.67 times 10 to the negative 11, big G. He's
so the
top.
gravitational force is 244.6 newtons. So that's how you can get the answer using that equation. It turns out that the
Okay, is there-
gravitational
It's not necessary to use this equation on the surface. What would you usually use to calculate? Don't tell me, but write it down. What's the usual equation you use on the surface of the Earth? You'll see that it's consistent. It should be the same or close to the same. How would you calculate the force of gravity on that block? It's a 25 kilogram block. What'd you get?
245.
Yeah.
That's the original.
Yeah, so you don't have to use this on the surface. Just use mass times 9.81. Use it for positions far above the surface. Yeah.
So R is the radius of the other object.
R is the distance from the object, this case the block, to the center of the Earth. Center of whatever the other object is. The distance. In this case, that's the radius of the Earth because you're right at the surface.
Okay,
Or
so
it's simply
if there were two radii, then you'd add them up.
Yeah, we'll deal with that later. You'll have, let's say, a block above the surface, and you'll be given the height of the block. You'd have to add that height to the radius of the Earth.
the weight force of the object. So the weight is simply mass times the gravitational acceleration. So we have a 25 kilogram mass, and the gravitational acceleration on the Earth is 9.8 meters per second squared.
You see 9.8, it's approximation.
So it's 25 times 9.8, and you get about 245 newtons. So these answers are about the same. So this is the most easiest way to find the weight force of an object on any planet if you know the gravitational acceleration of that planet. Now let's work on this problem. What is the force of gravity that is exerted on the Earth by the Sun? So we're given the mass of the Sun and the Earth and the distance between them. So let's start with the picture.
Okay, so we'll stop it there. Write this question down. Again, he's giving you the values, but you have those values in your table of constants, back of the formula sheet. Yes? Yeah, I think I can do it this way. This one? You use W for weight instead of F of G. It's the same thing.
Given the mass of the Sun.
Everyone got that? You're going to write down the question. Give it a try. See if you can do it. See if you can do it. I'll start it in a sec here. Okay, and again, I wouldn't give you these values like he did. They're in your data book or your table of constants.
And the Earth and the distance.
This is the orbital radius. What do you call the distance between the Earth and the Sun? That's an average distance, the orbital radius.
Between them. So let's start with the picture. So let's say that's the Sun, and this is the Earth. So the Sun is going to exert a gravitational force on the Earth. The Sun is going to pull the Earth toward itself, and the Earth pulls the Sun toward itself. Those two forces are equal magnitude but opposite in direction. So we need to calculate those two forces. Now we're given the distance between the center of the Earth and the Sun, and that's 1.496 times 10 to the 11 meters. We have the masses as well, so all we need to do is plug everything into this equation. So G is 6.67 times 10 to the minus 11, and the mass of the Sun is 1.99 times 10 to the 30 kilograms, and the mass of the Earth is 5.97 times 10 to the 24 kilograms.
Again, located in your
Divided by
data
r
table,
squared. So that's
table
the
of
square
constants.
distance between them. So you should get a gravitational force of 3.54 times 10 to the 22 newtons. So that's the force that the Sun exerts on the Earth, and it's also the force that the Earth exerts on the Sun. They're the same. Now let's move on to number 4. Planet X and planet Y have a mass of 3 times 10 to the 24 kilograms and 4.5 times 10 to the 25 kilograms. So let's draw a picture. So let's say this is planet X, and this is planet Y.
Okay, now a little bit of different calculation. Now you're not calculating the force, you're given the force. It's 3.6 times 10 to the 20. Now you're going to calculate the distance. You're going to have to rearrange for that. Give that a try. I'll include this video in mine. I'll put it in the link it. Remember, you got an r squared, so you're going to have to take a square root. You're looking at a fairly large distance, the distance between planets.
Now we're given the gravitational force between these two planets. Our goal is to find the distance between the two planets. And r is going to represent the distance between the center of planet X to the center of planet Y. So let's start with this equation. And let's rearrange it to isolate the r value. So I'm going to multiply both sides by r squared. So on the right side, these will cancel. And so I have f times r squared is equal to g m1 times m2. So next I'm going to divide both sides by f. And so r squared
Pause that.
is g m1 m2 divided by f. Now the last thing I need to do is take the square root of both sides. So r is going to be the square root of g m1 m2.
And you use the positive value. It's a distance. Find the positive value.
So let's go ahead and get the answer. So that's going to be 6.67 times 10 to the negative 11 multiplied by the mass of planet X, which is 3 times 10 to the 24, times the mass of planet Y, which is 4.5 times 10 to the 25. And then we need to divide it by the gravitational force that's acting on these two planets. And that's 3.6 times 10 to the 20 newtons. So the answer is about 5.0 times 10 to the 9. So it's about 5 billion meters. So that's the distance between the two planets, between the centers. Number 5, calculate the net force exerted on the moon when it's between the Earth and the Sun. And we're given the distance between the moon and the Earth and the distance between the Sun and the moon. So let's draw a picture. So we're going to say this is the Sun.
Try that one out. You'd be given the distance between, what is it? You're given the distance between the Earth and the moon, that's it. You'd have to be given the other problems to grab.
6.67.
Stupid string.
Basic number is 3. Other 3 grams. So we calculate twice.
Ah, got it. So we can use these for our experiment. Pipettes.
Break some plastic for someone's head.
You guys break that glass, I'll be mad. Yeah, it saves me getting the stuff. I'll use a pipette. It'll work.
Sun?
Yep. Now, let me skip ahead. Let me skip part of this. It's helpful though. Two good questions.
And this is the moon. And here's the Earth. Now, the sun is going to exert a gravitational force on the moon. And it's going to pull it towards the sun. Let's call it Fs, the force that the sun exerts on the moon. And the Earth also pulls the moon toward itself. Let's call it Fe. Our goal is to calculate the net force. The net force is going to be the difference between these two forces. Based on the way it's drawn, Fe is pointing in a positive x direction, so that's going to be positive, and Fs is in the negative x direction, so I'm going to put a negative sign in front of it. So because these two forces are anti-parallel, the net force is the difference between those two forces.
So yeah, he's lined it up. So if it works out that the force by the sun is greater, he'll end up with a negative net force. It's the way he wrote it.
Go ahead and calculate Fe first. So it's going to be G times the mass of the Earth multiplied by the mass of the moon, because this force is between the Earth and the moon, divided by the square of the distance between them. So that's 6.67 times 10 to the negative 11. The mass of the Earth is 5.97 times 10 to the 24. And the mass of the Moon is 7.35 times 10 to the 22 kilograms. And the distance between the Moon and the Earth, that's 3.84 times 10 to the 8 meters. So let's square it as well. So let's go ahead and type this in.
Hit emergency callback.
So you should get 1.985 times 10 to the 20 newtons. So that's the force that the Earth exerts on the Moon towards the right. Now let's calculate Fs. So it's going to be G times the mass of the Moon times the mass of the Sun divided by the square of the distance. So G is not going to change. It's the same value, 6.67 times 10 to the minus 11. The mass of the Moon is still 7.35 times 10 to the 22. And the mass of the Sun is 1.99 times 10 to the 30 kilograms. Now the distance between the Sun and the Moon is given to us. That's 1.492 times 10 to the 11 squared. So you should get a force of 4.383 times 10 to the 20 newtons. So now that we have these two forces, we can now calculate the net force. So the net force is going to be Fe, which is 1.985 times 10 to the 20, minus Fs, which is 4.383 times 10 to the 20. And so this is going to be negative 2.398 times 10 to the 20 newtons. Now the reason why we have a negative sign is because the net force is directed towards the left. Towards the negative.
So he ends up with a negative answer, indicating that the net force is to the left. This next problem is, okay, let's finish this one.
The next direction. And so what that means is that this force, Fs, is greater than Fe. So the gravitational force exerted by the Sun on the Moon is greater than the gravitational force exerted by the Earth on the Moon during a solar eclipse, for example, when the Moon blocks the Sun relative to the Earth.
He's talking about a solar eclipse. That's when the moon is between the earth and the sun, right? Moon blocks out the sun. Lunar eclipse. Look that up. I was in Utah when we saw the last one, right? We saw a solar eclipse. It literally you could see all these shadows start to form, and then all the insects and chirping of the birds just grew silent. And then you could look up to the sun, you could see. It wouldn't. I had special glasses to do it, that you could see the flare on the perimeter around the moon that blocked the sun.
So the moon is being pulled more towards the sun than the Earth. And the reason why that happens is because the mass of the sun is so much more larger than the mass of the Earth. Even though the distance between the Earth and the moon is a lot less than the distance between the sun and the moon. But the mass of the sun is just a lot larger. As you can see, these two values are very close. So the gravitational force exerted by the sun on the moon is a little bit more than twice the gravitational force exerted by the Earth on the moon. Nevertheless, in this situation, this force is greater. So the moon feels a net force that pulls it towards the sun. Number 6. What is the net force exerted on the moon by the Earth and the sun?
This is a good problem. We're going to have to do a similar one to this. So I usually cut it short here, but I'd like us to look at this one. This one, I would just, you might be able to do it. Let's just copy it down. Let's watch the steps and then copy his steps.
When the two gravitational forces acting on the moon are at right angles to each other. So how can we find the answer to this question? Well, let's draw a picture, just like we did before. So let's say this is the sun, and we're going to have to put the moon at this position. Let me draw a little bit bigger, and let's place the Earth here. Now we want the two forces acting on to be at right angles with each other. You could put the Earth here if you want to. It won't change your answer. Now the sun is going to pull the moon toward itself. And the Earth is going to pull the moon towards the Earth. And so these two forces are at right angles. And so there's going to be a net force that is going to be directed in that direction. Now we know the force of the sun exerted on the moon is going to be greater than the force of the Earth exerted on it. And based on the last example, the values shouldn't be that different. So let's rewrite the values that we had in problem 5. Fe was 1.985 times 10 to the 20 newtons. And Fs, that was 4.383 times 10 to the 20 newtons. So let's calculate the net force.
So he's just used the same distance as before, except now instead of the Earth being here, the Earth is now down here. Same distance though from the Earth to the moon and the moon to the sun. So he can use the same values. Yeah? He's just saying if it's that, given that it's 90 degrees. And that happens sometimes, right? So given that it's 90 degrees, what is the net force on the moon? Due to the force of the Earth and the force of the sun acting on it.
So here's the net force. It's going to be the hypotenuse of the right triangle. Fs is in the x direction. Fe is in the y direction. So regardless of how you draw it, you can also draw it this way if you want. You can say here's the net force. Here's Fs. And this is Fe. This is still the hypotenuse.
Yeah,
so
he made
that force.
He made a little mistake here, right? Fs should be to the left, but that's fine.
Is going to be the square root of the square of Fs plus the square of Fe.
These numbers you already have from the previous problem.
383 times 10 to the 20 squared plus 1.985 times 10 to the 20 squared. All right, so let's go ahead and get the answer. So the net force is equal to 4.812 times 10 to the 20 newtons. So that's the net force acting on the Earth, on the moon, when it's at this position.
Yep. Oops.
Position force.
Okay. Let's look at number 8. I'm just going to give you the answer to it. I'm going to go on to some gravity problems, or at least one gravity problem. Give you the answer to this. The answer to this is 21 meters per second. No? Yeah, that's what it is. Okay, now we're going to go on to a slightly different problem involving gravity. Just want to add this to what you already have. It's another example. Actually deals with what Jake was hinting at. Okay, see if you can do this. We'll go through it together, but try it first. Calculate the gravitational force which is the same thing as weight, on 600 kilogram spacecraft. That is 16,000 kilometers. Above the Earth's surface. Okay, so see if you can do it, and then I'll draw the diagram for you. Let's see if you can get that. If you're listening when I explained it briefly to Jake, what you got to do. You're above the surface, that's the value they gave you. Yep. This is it. This one? That fine or what? Is that okay? Oops. That's question 2.
Yes.
Yep. Okay, so that's the FG or weight.
So can I, like, if I convert the kilometers to meters, like, how many should I add to the scientific equation?
How many meters are there in a kilometer?
Thousands, like
How many zeros is that?
3 to 7.
Add 3. What is R in this? Let's take a look at the diagram. R is always the distance from the center of the Earth, or whatever planet, to the spacecraft, which is far above the surface. What do we have, though? What we're given is the height, 1.6, 16,000 kilometers, which is, to find it in meters, multiplied by 1,000. Just 16 million meters. Quite high up there. What do I know about? This is the radius of the Earth, which you get, radius of the Earth you can get from your data table. The radius of the Earth is 6.37 million. You have to add them together. This is the height. So what does this R equal? This R is equal to, you have to add the two distances. Add the radius of the Earth to the height. So FG becomes, again, it doesn't matter what you put first, mass of the Earth or mass of the satellite. 600.
Seven.
480 newtons. Don't forget, add the radius to the height. And convert kilometers to meters by multiplying by 1,000. Okay, we don't have, I want to give you about half an hour to study for the test, go over the solutions I gave you. Do page 235 first. Shouldn't take you that long. Do that. Work on that first. Do at least the first three. If you find it's getting close, you got about another 7 minutes to the half hour. If you find you don't get it all done by 11:30, you can just come back to it tonight. Yes? Yep. You want it bigger?
Is there anything else now?
So work on page 235, 1 to 5. And yes, when we get closer to the half hour, you can start studying for the test if you want. I may be giving you too much time. That's okay. That is more than enough. I'm going to get ready for the lab.
What did you write before this example?
Just the answer to number 8. Yeah. Get stuff done. I think the lab. Okay. Anyways, we'll be okay, I think, for tomorrow. Everyone got it? Anyone still copying down? Okay, guys, can you just turn off that?
1.6 yeah. Two.